Alex Matrosov, Philip Lebedev, Yegor Vasilenko, and Andrei Labunets present Static Analysis Base Recovery of Service Function Calls Type Information in UEFI firmware. Reversing UEFI firmware requires a lot of background and knowledge about firmware and understanding of hardware before you can start hunting for vulnerabilities. With this new tool, you can automatically recover service call and EFI type info so that firmware code looks like the original source.
Hello, Ekoparty, and it's a big pleasure for us for presenting on this pandemic edition. So I think it's very important to support the conferences in these difficult times, and it's not my first time on Ekoparty, and I always appreciate very advanced technical audience here. It's why we decide to present about our EFI Explorer tool exactly on Ekoparty. And our talk is actually about different static analysis techniques for recover the type information and service function calls from UEFI firmware. And I want to introduce UEFI Explorer team. It's Yegor Vasilenko, Philip Lebedev, Andrei Labunets, and myself, Alex Matrosov. So motivation of this research, it's been pretty simple. We basically, all of us working on UEFI reverse engineering for quite a while, and we noticed that it's not a lot of automation tools available on the public. So it is, of course, very good plugins available, but unfortunately, they mostly support one single function implemented on particular plugin, and it's solving just one problem. We don't find combination of all tools we needed in one set. And also, most of these plugins not supported for a year already. And of course, it's hard to use a new version of IDA Pro and other reverse engineering tools. It's why we basically focus on developing our own to benefit us, and not only us. We focused on benefit for all the reverse engineering community to provide them helper tool, which will be making UEFI reverse engineering easier. But why it is important to have a UEFI reverse engineering tool, and why you need to focus on UEFI firmware reverse engineering. Last year, I've been presented keynote on Ekoparty about the advanced threats evolution and researchers arm race, where I've been focused on many different topics and why persistent vectors will be focused in the future, and actually already focused now on the firmware and hardware more than operating system level. Basically, other side of this, it is a supply chain problem on UEFI ecosystem, where we have multiple vendors and also frameworks like a Phoenix, Insight, and American Megatrends, where basically these vendors develop kind of like universal framework. It's get customized by device manufacturers or original equipment manufacturers like Dell, Lenovo, and HP, but in the end, they contribute less than 10% of the code base, and most of the code, it is Intel reference code, EDK2, or AMD if it's AMD-based platform. Other big part of this code is the framework from Phoenix, Insight, and American Megatrends, and we need to understand actually and go deep on vulnerability hunting to understand how these issues can affect different platforms, and basically what the coverage are and what is the exact impact. It's where we need advanced reverse engineering tools, and basically we need to investigate how the impact with the persistent vectors affect modern platforms. But unfortunately, I would say the classification of the firmware corruption attacks and persistent vectors, it's not really correct on current Mitra attack framework, because it's mostly focused, you need to check the integrity, but the integrity doesn't mean much about actual impact. So if the integrity is broken, you don't have the full visibility on the impact, and you can't understand what exactly happens. For that, you need to go deep with reverse engineering tools and basically understand what the actual problems. The mitigations provided from OS privileges to reducing some drivers and other things, it's actually not equal with the firmware privileges, which I would say don't solve much problems there. You can block something on the operating system level, but for the firmware and hardware world, physical attack vectors, it's quite huge. Updates coming from some vendor sources, but who proves this vendor source is secure? So basically, we trust too much everything which is coming from the signing source, right? So we have a binary blob which is signed by trusted vendor and we trust it by default. I would say antivirus industry in the past, probably during last 15 years, learned hard lessons about the signed binaries and trust. But why we not rethink the same thing about the firmware problem? Basically, we blindly trust anything which is come from trusted source and sign it, right? And it's create a lot of circumstances and concerns for basically go over and dig on it. So it's why we start working on EFI Explorer. Think about, we simplifying reconstruction UEFI specific types and protocols with EFI Analyzer. We create unified loader, which is basically try to load the whole firmware image and rebuild all the dependencies between different drivers. As example, you have the protocol called, the protocol, let's say it's kind of like same thing as an API function in operating system binaries. And when API call happens, it doesn't mean the implementation of this protocol implemented as the same one binary. But you need to find this binary where this protocol is implemented to understand the full workflow for security feature or something. So it's why these cross-references on the whole firmware image make a lot of sense. And where actually EFI Explorer stand for. And last thing, we basically develop kind of like a vulnerability analysis patterns with UEFI specifics and power of the static analysis, and we call it Vuln Hunt. So basically, our vision to turn UEFI into the white box. Of course, like white box, it's very powerful word, but at least we try to make it as a white box, simpler as a white box for reverse engineering. Okay, and here is architecture of EFI Explorer Analyzer, and you can see a lot of different features is implemented, and Igor will be continue on it.
Hello everyone, I want to tell you about EFI Explorer Code Analyzer. In UEFI firmware images, data type information plays a very important role. With all the type information applied correctly, you can do a very high quality static analysis. Let's take a look at a simple example. The first figure shows part of the code of some function in UEFI without any processing. The second figure shows the same code snippet when casting a global variable to EFI system table data type with pointer. You can see that simple casting of a global variable to the required type makes the code much clearer. EFI system table is one of the basic data structures used in UEFI. The EFI system table pointers to the boot services, runtime services, and other important fields. The slide shows a list of basic data structures to which we convert global variables. Automatic search for global variables with these types is the starting point for further analysis. A huge advantage when analyzing UEFI drivers with IDA Pro is that IDA Pro has default type libraries specifically for UEFI drivers. They are contained in the UEFI and UEFI 64 TIL files. This slide is on the types from EDK2. Considering that almost all vendors use EDK2 to develop their firmware, these TIL files should be enough to analyze most UEFI firmware. Currently, we have a number of methods to search for different types of global variables. Some of them are very specific and more complex than others. So let's not go into details about all methods. Instead, I will focus on one technique that we use to find the global variables GST, GBS, and GRT. For each UEFI driver, the entry point is the module entry point function. For drivers such as Dixie or SMM, the arguments to this function are image handle and system table. In some cases, such an entry points look like one shown on the figure. This is a simplified example. We can analyze the entry point and define 4 global variables at once from the input data. But there are also more complex examples that are much common in the practice. The figure shows one of them. In this case, the analysis of the entry point does not provide us with any important information. How to solve this problem in general? Let's start by looking for the global variables GBS and GRT. As noted earlier, pointers to the EFI boot services and EFI runtime services tables are contained in the EFI system table structure. The slide shows a section of code in which the global variables GBS and GRT are initialized. For clarity, this code has already been analyzed using EFI Explorer. To find GBS and GRT global variables, for 64-bit drivers, you need to look for the instruction set shown in the slide. At this stage, we have learned how to find all the global variables GBS and GRT. To find the GST variable additionally, you need to find the instructions shown on the slide. Keep in mind that we should search for those instructions in the code that precedes the instructions for filling in the register with GBS and GRT addressing. Having analyzed the entire driver code in this way, you can find several global variables GST, GBS, and GRT at once. Our plugin automatically casts global variables to the desired type, which makes the code readable. The example shows the main idea of how we search those global variables. Actual methods are slightly more complex, and there are many edge cases we handle separately. For more details, feel free to take a look at source code in the repository. Our plugin can find boot services, runtime services, SMM services, and PI services. The figure shows the search result. The search for each type of service is similar. Let's take a look at it using boot services example. Consider the code snippet shown in the figure. Suppose we have already defined the global variables GBS as shown in the previous step and want to understand which of service calls is made to a specific address. The RAX register contains the base address of EFI boot services structure. Accordingly, the create event service is located at the address RAX plus 50H, since it is located offset 50H at EFI boot services structure. Based on this principle, we search for all boot services. The algorithm is shown on the slide. This is what EFI Explorer does to find boot services calls. The first figure shows a code snippet from the example after the plugin is running. The second figure shows the same code in the decompiler. We examine the algorithm for finding services calls using the example of boot services. In the case of runtime services, SMM services, PI services, the algorithm is similar. Some edge cases are not being handled at the moment, but we are aware of their existence. For example, passing control to a service via jump instruction. Another feature of EFI Explorer is to recognize EFI protocols associated with boot services and SMM services. The EFI protocol consists of an identifier, protocol GUID, and the protocol interface structure. There are some services in UEFI designed to work with protocols. The slide shows a list of such services from EFI boot services and EFI SMM system table. Suppose we have already found such services in the code of the driver being analyzed as described in the previous step. Let's look at the call to the locate protocol service, which is shown in the figure. The first argument to this function is the protocol GUID to locate, and the third argument is the protocol interface. There are some similarities here with the co-get class object function from the component object model. From the input parameters to the locate protocol function, we can easily get the variable of the protocol GUID entry. Then, using the GUID, we can understand what kind of protocol it is. To do this, we look for the given GUID in the prepared dictionary of GUIDs. We moved this dictionary to GUID JSON file. If the GUID is found, we give the protocol a name and put it in the list of found protocols. If the GUID is not found in our dictionary, we consider it proprietary and call it proprietary protocol. We perform similar actions with each of the listed services. The only difference is in which argument the protocol GUID is passed. As a result, we get another window EFI Explorer protocols, which contains all protocols GUID, their names, services that work with these protocols, as well as the addresses of the protocols GUIDs in the data segment. Identifying protocols is a very useful feature to understand cross-references between different UEFI executables. Having information about the protocols, we can understand in which driver a particular protocol was installed using the install protocol interface or install multiple protocol interfaces services, and in which driver the same protocol was obtained using the locate protocol or open protocol service. This will help us to trace the sequence of execution of the UEFI drivers. GUIDs in UEFI are very important. We have already covered how GUIDs are used in identifying protocols, but in fact, they are used when working with many things in UEFI, with events, variables, images, and so on. This is why EFI Explorer has a feature to search for GUIDs among local and global variables. The search is carried out using the same dictionary from GUID JSON. It is located in a separate file for better extensibility. As a result of the plugin work, all found GUIDs will be renamed and placed in a separate window, as on the slide. I partially talked about the features and the internal structure of the EFI Explorer analysis engine. You can see everything that I have not told in the source code. Now I will hand over to Philip, who will tell you about the loader. What is it, how it works, and why it's so important.
Hi everyone, my name is Philip, and I'm very happy to introduce the second part of the EFI Explorer, which is responsible to load and analyze the all firmware. But first of all, let me just share a few thoughts about the UEFI firmware reverse engineering, exactly how the UEFI firmware reverse engineering looks like. Everybody knows that the common UEFI firmware steps for reverse engineering are next. Firstly, UEFI firmware is loaded into the UEFI tool or another kind of software which is responsible to parse and iterate through Dixie and SMM, Dixie combined drivers, etc. Then the security expert chooses which driver is more interesting to investigate and extract it. And then the extracted driver is loaded into the either Pro or GDRA. But let's imagine if the all image can be loaded and investigated as a single binary, like dropping the all UEFI firmware into the either Pro instance and reverse it. Actually, this idea is not new and was implemented in the project named GDRA firmware utilities, which is very cool. But unfortunately, such loader exists only for GDRA, and there is no possibility to create data code references between different drivers. But it's very important because there are so many interactions and dependencies between different drivers. For example, like already mentioned, UEFI protocols, registration, locating, which are very important during firmware investigation. And now, I would like to introduce the core features of EFI Explorer, which is responsible to simplify the way of UEFI firmware reverse engineer. EFI Explorer, as it says, is an IDE Pro loader model, which makes possible to load each 64-bit UEFI driver into a single IDE database. Current version of EFI Explorer uses UEFI tool parser engine, which handles all UEFI parsing routines, and each expert can easily navigate within the all UEFI firmware and investigate each UEFI driver. If you close look on the slide, you can see that each driver is located in separate section with data and code embedded, so we can easily navigate from driver to driver and make references between them. By the way, it's very important to notice that EFI Explorer identifies each driver entry point that provides a choice for an expert where to start reverse engineering. But the most significant feature is that most of EFI Explorer features are supported by a loader. So core UEFI structures like boot services, runtime services, well-known proprietary protocols can be identified within the all firmware. And now let's talk about a bit more about the protocols registration and usage. As I said before, protocols are key objects which are processed during firmware execution. And there is a well-known case when some protocols are registered and used in different drivers. The old way of protocol interface identification is to iterate through a list of drivers and find out which one is used for registration or which one used for the locating. But the new way is just to trigger EFI Explorer on the full UEFI image and navigate from the address of registration and the address of usage. And now I would like to show you how it looks like. Consider we got a next feature. As far as we know that EFI Explorer constructs a table of services which can be executed within the firmware. It's easy to see on this slide that some proprietary protocol GUID used for installing and locating protocol. For example, on this slide is marked by blue color the GUID with protocol which is installing interface, and one which is below it, it's just locating protocol. But if we look closely on the left column, we can identify that the addresses of each reference are pretty different. So it closely looks like it's different drivers using the same protocol. And let's navigate to each of these references. According to the next picture, we can define that this protocol used by two drivers. All of them are based on the AMD name, so we can easily identify that there are pretty different two drivers, but using the single GUID protocol. And now let's just go further and identify which interface is used for the registration. When we locate to driver where install protocol interface is triggered, the global variable passed to this function points to the interface. That means that protocol interface is identified. It can be used like reference when we look at another driver located by this GUID. And on the next picture, we can identify the global variable. Well, this keyword is points to. Yes, on this picture we can find out exactly the same reference and information about the interface. But now I would like to continue with more interesting features like vulnerability discovery using the EFI Explorer plus EFI Explorer. And now I would like to talk about more closely about the SMM callouts identification. Every firmware security experts know that the SMI handler is a place where SMM callouts may occur. But let's just remind to each other how the SMM callouts exploitation looks like. Assume we got a simple example like presented on the slide when we got a runtime service get variable which is triggered within the SMI handler. That means that the attacker with root access can run malicious code with SMM privileges. To achieve that, that is necessary to identify the runtime services address. It's pretty easy with the help of EDK shell and command memory, which just prints information about the system table address, runtime services, boot services, and etc. And usually, unfortunately, such addresses are not changed across the system reboots. So the attacker can store the address value and use it during the exploit development. Everybody knows about the ChipSec framework. It's a big help in exploitation and proof of concept development writing tasks. So to write an exploit or the proof of concept, the attacker needs two things. First one is to prepare memory region with a shell code. And the second one is to override get variable runtime service by the shell code. But we need to keep in mind that the address of the get variable and runtime services already known. So you can just keep close look on the slide. You find out that the address, and we got a plus 40 hex 48 just to point to the get variable. So we're writing where we override the address by our shell code. And the last step, and the final step, is just to trigger SMI handler followed by the malicious get variable function. And finally, we can say that attacker will achieve the SMM privilege escalation with code execution. And now I would like to talk about how such cases can be easily identified and investigated with the help of EFI Explorer and EFI Explorer. We introduced the semi-automatic way of SMM callouts identification within the all firmware using static analysis. Since EFI Explorer can trigger EFI Explorer analyzing routines, it's possible to identify different runtime boot services executing within the SMM. Let's just remind how the SMI handler can be registered. On this slide, we can find out the EFI SMM SV dispatch protocol registration, which got two functions like register and unregister. So we can easily just iterate through the code base of the UEFI firmware and identify each place where the register function is called. And now let's look at the disassembled view of the how this function can be triggered within the UEFI firmware. On the next picture, we can find out that the register RDX can be used for the storing the SMI handler pointer. So if we just collecting the RDX value, we can store the address and just collect it into the database, just marking that this function is SMI handler. Yes, it looks by this view. So we got a RDX, and now we can just make a close look at the decompiled view, where we can find out that the second argument is indeed the SMI handler pointer. Right, yes, and yes, it's called register function. So, and now I would like to introduce how this can be collected during EFI Explorer execution. On the left side, we got we're just triggering the EFI Explorer when the UEFI firmware is already loaded into the IDA database, just triggering the EFI Explorer plugin. And on the right side, we can see just produce the table with the enumerated SMI handlers. So now I would like to introduce the small demo, which shows how it's pretty easy to identify using the EFI Explorer SMM callouts. So now we're just doing the similar thing. We just identified the SMI handlers and found out the similar bug when the get variable just triggered within SMI handler. And we can mark it like SMM callout. So we just used for about, how much? I guess about the 4 seconds to identify the bug. And the firmware, when we just looked at it, it seems like was there pretty fresh, and it may be just a 0 day on the previous demo. Yes, and about the limitations, there are two key limitations which we'll try to resolve in the future. First one is that the EFI Explorer does not support BE and 32-bit drivers, and they may occur some rare false positive references when the driver got a fixed base address, but on the next I will show you how we'll try to resolve this in the future. And about our future plans. Yes, first we need to add the 32-bit binaries. Maybe we just can convert them from 32 bits to 64, or just to ask user to select from 32 bits to 64. It all depends on the community. The second point, we will add the relocation section patching, which can resolve the issues when the driver got a fixed image-based address. And we'd like to add two more features, like embedding n variables into the database, just to make references between the Dixie, between the drivers and n variables, just to investigate the code base when maybe some kind of security issues, when driver got a wrong handling the n variables. And next one, tried statically to match the SMI numbers and the SMI handlers in static way, so it can really simplify the way to write the proof of concept or exploit template without access to the real device. And now I would like to give the floor to the Andrew with his topic.
Hello. So now that we know how to basically do the fundamental analysis and to understand how firmware works with the context of the whole image, the next question is to understand how good EFI Explorer is at doing its job. And on the next slide, you can see that there are some basic, really most important functionalities by the EFI Explorer. It's recovery of global variables, system calls, and protocol GUIDs. So let's evaluate them. But before we jump to evaluation, let's ask ourselves, what are the most important things about UEFI firmware compared to the reverse engineering in general and static analysis in general? Well, there are at least a few points we found interesting. First, there is on the previous slide, I will probably explain a little bit more that the UEFI firmware code base is mostly kind of unchanged. It's shipped with the very limited number of compilers and options. Also, there is very limited number of vendors because the ecosystem itself is very tight and there is a lot of dependency on hardware manufacturers. And as you know, there is not so many of them. So there's a little bit harder to get into that game. And so the code bases are predictable. As Alex said, there is a lot of reference code and a lot of EDK in the vendor shipped firmware. And there are other things. One of them is, for example, that, well, obviously, disassembly is important to annotate, even if we found a good way to translate it to some intermediate form. Well, the explanation for that is pretty straightforward. The code runs close to machine, so machine code is important. In particular, register specifics and instructions is important for the boot stage. Okay, now how do we judge correctness of the automated UEFI analysis with those assumptions? And on the next slide, there will be some more information about that. Basically, there's a whole range of powerful and rich methods of, let's say, logical reasoning about UEFI code. We found that in this particular situation, this might not be the first most optimal choice, and we decided to treat EFI Explorer object recognition as just a probabilistic algorithm, so that can recognize object with some probability. Then we evaluated with statistical methods on a data set of UEFI binaries. So more precisely, it's about collecting data, it's about collecting labels, and it's about picking up the metrics and finding proper summary statistics. So let's walk through our approach in detail. Let's talk about data. So if we talk about data sets, data set is a set of UEFI binaries, UEFI modules compiled from something. This data set should approximate UEFI firmware in the wild. It should be as close as possible to what people reverse engineer in reality, so that code compilation and linking options and shared code usage and code pattern distribution and distribution of system calls should be as close to reality as possible. But most importantly, the data should have ground truth labels. Remember, UEFI is kind of a black box-ish, so that it's everything. Not a lot of code is shipped as a source. So those conditions and those constraints, and also our desire to be transparent and open in our measurement, narrowed down the search to pretty much small amount of known open source projects, EDK2, UDK, and Core Boot, and similar things. Their default tool chains are pretty close to what vendors use, and also you can take different versions and different branches, cut them, and obtain more samples. So our initial measurements are currently done on 186 EDK2 models for x86 architecture. But of course, it's just a start. Now let's talk about labels. That's a more interesting thing. Basically, labels are something which tells us that the object we want to recognize, the object we recover, located at a particular offset. One straightforward way is to get debug symbols. That's pretty clear. But that method does not allow us to get a granular understanding where the, say, function pointers are, or at least we have not found the way at this point. One trick with using debug symbols is that we just load it into IDA and avoid some dependency on, say, proprietary formats such as PDB. And let's just let IDA do all the heavy lifting. Then we use IDA to extract all locations of global variables. And then use EFI Explorer, run it on the same binary without debug symbols, compare and diff the results. All good. There are some disadvantages. It's most importantly, as I said, locations of function pointers are unclear, and it's also not fully transparent whether debug symbols actually affects code generation in any way, so that it biases or changes our dataset in ways we could not anticipate. There's a second way we found. It's basically asking a compiler to generate assembler listing, to annotate it with a source code, and then use this annotation in order to map objects, the desired objects we want to recover, to a particular offset. Also pretty clear. But we found that line annotations, even though generated by the compiler, are also sometimes incorrect. And also, writing assembly listing parser kind of brings an interesting chicken egg problem, because the near perfect label generation can also have bugs, and now we have to figure out whether our labeling system is correct. But anyway, that method works for us in practice. Okay, and finally, let's talk about how we diff the results, calculate the metrics, and pick the summary statistics. Metrics, the goal of them is to reflect the overall goodness of analysis. Basically, how do different types of objects affect the measurement? Well, we found it reasonable to measure each group separately. So we measure recognition of global tables, recognition of the system calls, and protocol GUIDs. Why? Well, there are a few points, but I found one most beautiful. It is that some objects are proxies for recovery of other objects. So think about recognition of service call, protocol-related service call. After EFI Explorer finds a service call, it marks a protocol GUID as an argument, and only after that, that protocol GUID is considered recognized. Now, that number of those protocol GUIDs is a kind of a proxy metric for the recovery of boot services calls. We have two metrics. Basically, cross-referencing those two metrics lets us infer some additional insights. For example, we now know how exactly our labeling system works and whether it's correct or incorrect. But okay, let's jump to the most important question: what metrics works best for our case? So we use a precision and recall, which shows performance for common UEFI binaries, and also false positive rate. Now, how do we average the results? Well, we found that just taking the average and weighted average of precision and recall is good for start. Just as a reminder, precision shows the probability that the recovered object is actually exists in that place. And recall is the chances that all recovered objects which are actually located in the binary will be recovered by the EFI Explorer algorithm. Let's talk about the results. This is basically our current measurements. Most important thing is that our EFI Explorer surprisingly works pretty well. It is able to recognize a lot of objects with high precision, which means that if it recognizes an object, it likely exists. Recall is slightly less for all objects, so manual work is still required. But when you get some summary statistic or some average number, the next question is, okay, what's behind it? What's the distribution behind it? This slide shows not necessarily the distribution, but a way we understand what is behind this precision and recall numbers. We just sort precision for each module and show the blue area, which shows all the modules which have perfect precision. And on the left, where there is an orange area, there are modules which kind of do not perform well in terms of precision. This particular way of looking at the situation helps us to debug what is the most common problem with those modules and what is the most common problem with the analysis we face, so that we fix it and improve our algorithm. The same is with recall. Yeah, we can go to the next slide. Basically, let's try to summarize the results. As I said, EFI Explorer is very good at finding location of objects, and when it finds them, it's very likely that the object is valid. It's better at finding global variables. It's a little bit worse at finding function pointers in protocol GUIDs. You can see that the precision from the fact that the precision and recall for global tables is slightly larger than for function pointers in protocol GUIDs. Next, if if the labeling system is slightly unpredictable, it becomes harder. In our case, we found that, surprisingly, the granular labeling system for objects, namely for service calls and for protocols, is actually quite hard, even though we have full control over the code, over its generation, even with the source code. For example, protocol and non-protocol GUID ambiguity takes a little bit of additional whitelisting and blacklisting and a lot of case-per-case adjustments. And of course, manual work is still needed to complete annotations. But that's how all plugins work. So our EFI Explorer saves a lot of time by finding most of the objects. And since the precision is pretty high, those objects are valid. What's left is just to verify what else is in the binary. And finally, we are working to release this evaluation system in a stable state. Let's go to conclusion. Our main point is that it's actually right time for a much broader audience to look into the UEFI threats. I mean, broader, more than a selected number of very smart and talented UEFI and firmware reverse engineers. It's not complete mystery what is inside UEFI. You can reverse it. But when it comes to the threats, UEFI threats and potential implants, I would say God knows what's there. And it's interesting, and it's the right time to look into that. Our EFI Explorer helps to do that from a static analysis perspective. Next point is that well-tuned heuristics actually work surprisingly well for UEFI, including automated vulnerability finding. Analyzing binaries in a single context altogether for the whole binary, for the whole firmware image is tricky. It takes a lot of time, but it's really worth it. Also, thanks to some early smart decisions, our plugin is blazing fast and very scalable. So if I recall, for some cases, you can analyze the whole firmware image, including all of analysis, in a matter of a few seconds. To our knowledge, this is the first UEFI reverse engineering tool where we rigorously evaluated analysis quality. We tried to do our best, but maybe it's not perfect at that time. Let us know if you like it, and we'll definitely release a more transparent and more open way to do that so that you can have reproducible results. And finally, I would say that security research of BIOS, and especially its automated firmware reversing, goes for pretty long. At least the first paper I remember goes back to 15 years. Maybe there are some earlier research. So a lot of good ideas are already there. We just try to make it a little bit better by combining all of the ideas and presenting some of our own ideas in a single place, and basically helping the community. If you have an idea, or if you want to inspect our code in detail or anything, feel free to go to our GitHub. And I also want to especially thank our contributors, our contributor Rolf Rolls, for code, for the contribution, and for very insightful and deep suggestions and discussion. Thank you, Rolf. And thank you all for your time and for your attention.
Thank you, Ekoparty. It was great. And yeah, so see you next year.